now was a demonstration of the power and speed of an automobile. Probably one day you too would like to possess a racing car or motorbike and go zipping. But do you know what actually makes an automobile move? Probably you would like to know. So we have here our friend and expert, Kirit Singh, to take you on this fascinating journey into the world of automobiles. Kirit.
Hello. Thanks, Nikhil. All automobiles, be it a family car, three-wheeler, two-wheeler, scooter or motorbike, have an engine which is the source of power. This is what makes the automobile run. Let's take a look at the engine of this one.
The engine is usually referred to as an internal combustion engine. This is because the fuel is burnt inside the engine, within the engine cylinders or combustion chambers. A movable piston fits snugly into the open end of the cylinder. When the piston is pushed up in the cylinder, the air-fuel mixture in it is trapped above the piston and is compressed. At this stage, a spark is fired, and this ignites the charge of highly compressed air and fuel vapor. The combustion or burning of the petrol creates high pressure, forcing the cylinder out of the piston. This movement of piston causes a shaft to turn or rotate. The rotary motion is carried to the car wheels by the powertrain so that the wheels rotate and the car moves.
The rotary motion is carried by the drivetrain of the vehicle to the rear wheels, and this drives the wheels and moves the car. Now, for the combustion of the fuel and air to produce enough power, the fuel and air must be in the correct proportions and must burn quickly and efficiently. Also, the requirements of the engine vary with the load, and the proportion of fuel and air has to be altered to meet these needs. This function is performed by the carburetor.
A simple carburetor could be made from a round cylinder with a constricted section, a fuel nozzle, and a round disc or valve. The round cylinder is called the air horn, the constricted section the venturi, and the valve the throttle valve. The throttle valve can be tilted more or less to open or close the air horn. As the air flows through the constriction, a partial vacuum occurs in the venturi, just where the end of the fuel nozzle is located. The other end of the fuel nozzle is in a fuel reservoir called the float bowl. With the vacuum at the upper end of the nozzle, atmospheric pressure pushes fuel up through the nozzle and out into the passing air stream. The fuel enters the airstream as a fine spray, which quickly turns into vapor as the droplets of fuel evaporate. The more air that flows through the air horn, the greater the vacuum in the venturi, and the more fuel delivered, varying the air-fuel ratio or mixture strength. For the engine to tick over smoothly and pick up readily as the throttle is opened, the richest mixture of the whole range when the engine is hot is required, usually of the order of 11:1 in air-fuel ratio. When cruising, the mixture should be as lean as possible for economy, while maintaining smoothness of running and freedom from hesitation and surging. At this stage of cruising, the air-fuel ratio is between 16 and 18:1. Maximum power at full throttle, regardless of engine speed, always demands a richer mixture than when cruising at part throttle and is generally to the region of 14:1.
Thus, the fuel system must vary the air-fuel ratio to suit different operating requirements. The mixture must be rich, that is, have a high proportion of fuel for starting, but must be relatively lean, which means having a lower proportion of fuel for part throttle and intermediate speed operations.
This graph shows typical air-fuel ratios as related to various speeds. In the example shown, a rich mixture of about 9:1, that is, 9 parts of air for each part of fuel, is supplied for initial starting. Then, during idling, the mixture leans out to about 12:1. At intermediate speeds, the mixture further leans out to about 15:1. But at higher speeds with a wide open throttle, the mixture is enriched to about 13:1. Opening of the throttle at any speed for acceleration causes a momentary enrichment of the mixture.
You may be wondering why the engine requires rich mixture at the time of starting and at full throttle open operations.
This is because initially the engine and carburetor are cold, the airspeed is low, and much of the fuel does not vaporize. Thus, an extra amount of fuel must be delivered by the carburetor so that enough will vaporize for starting. Likewise, sudden opening of the throttle for acceleration allows a sudden rush-in of air. Extra fuel must enter at the same time to provide the proper proportions of air and fuel to the engine. To provide the extra fuel required, carburetors have accelerator pump circuits. It includes a pump plunger, which is forced downwards by a pump lever that is linked to the throttle. When the throttle is opened, the lever pushes the plunger down, and this forces fuel to flow through the accelerator pump circuit and out of the pump jet. This fuel mixes with the air passing through the carburetor in the right proportion. Thus, to produce sufficient fuel flow during the cranking, the carburetor has a choke. The choke consists of a valve in the top of the air horn, which is controlled mechanically or by an automatic device. When the choke valve is closed, only a small amount of air can get past it. It means the valve chokes off the airflow. Then, when the engine is cranked, a fairly high vacuum develops in the air horn. This vacuum causes the main nozzle to discharge a heavy stream of fuel. The quantity delivered is sufficient to produce the correct air-fuel mixture needed for starting the engine. Mechanically controlled chokes are operated by a pull rod on the dashboard. The pull rod is linked to the choke valve. When the rod is pulled out, the choke valve is closed.
With this arrangement, the driver must remember to push the choke control knob back in the de-choked position after the vehicle starts. If he forgets or fails to do this, the mixture will be too rich for the engine's needs and the engine will overflow, and in the long run this will cause carbonation, excessive carbonation of the valves, piston rings and spark plugs. Because drivers often forget to de-choke the engine, modern cars now have automatic choke mechanisms.
The automatic choke includes a thermostatic spring and a vacuum piston, both linked to the choke valve. The thermostatic spring is made up of two different metal strips welded together and formed into a spiral. Owing to differences in expansion rates of the two metals, the thermostatic spring tends to wind up or unwind with changing temperatures. For example, when the engine is cold, the spring has wound up enough to close the choke valve and spring load it in the closed position, and vice versa. Air can also be choked in a very simple way with the palm of the hand to start the engine.
It is very difficult to obtain the optimum mixture strength under all conditions of operation. To achieve this, it requires the addition of various extra devices on the carburetor, and these are designed principally based on what the customer is willing to pay. Also, since modern legislations dictate certain minimum standards for exhaust emission, complex carburetors had to be produced to meet these standards.
It is essential that the float chamber of a carburetor be vented. If this is not done and the engine is stopped when very hot, the heat tends to soak through to the carburetor bowl, causing the petrol to boil and foam. This would make the petrol percolate into the induction system, thus over-enriching the mixture. If the float chamber has a vent opening to the atmosphere, it can become choked with petrol foam, causing a back pressure, forcing extra fuel out through the jets, thus again over-enriching the mixture. If the vehicle is used in this condition, it can result in hesitation or total stoppage of engine in extreme cases. Hence, many carburetors have vents opening internally into the carburetor air horn. This creates a balance of air pressure between the float bowl and the air horn. Such carburetors are thus called balanced carburetors. Apart from having a vented float chamber, a balanced carburetor has calibrated fuel jets to maintain the optimum mixture strength in relation to speed and load. Very simple carburetors have only two jets, one the main jet and two the idling jet. More jets can be incorporated for operation at maximum power, cruising, slow running, and for acceleration. During idling, the throttle will be almost completely closed, so the velocity of the airflow through the venturi will be too low to develop depression sufficient to draw off any fuel through the main jet. To overcome this, the carburetor has a circuit called slow idling circuit. The atmospheric pressure pushes air and fuel through the passage as we see here. They mix and flow past the tapered point of an idle adjustment screw. The mixture strength can be adjusted by this screw. In such carburetors, the takeover by the main jet from the slow-running jet can occur smoothly, since as the velocity of the airflow through the venturi increases, so also does the depression over the main jet until it exceeds that over the slow-running jet, which therefore can no longer deliver any fuel. To allow extra air to enter the induction system to weaken the mixture appropriately, hydraulic devices in the form of compensating jets, as in the Bavaric compound jet system, have been incorporated. As the fuel is drawn out faster from the main jet, the level in the compensating well falls. This reduces the flow of fuel through the delivery pipe joining the compensatory well and venturi. This method is now almost universally used. An emulsification arrangement is introduced to obtain the same effect. The emulsion holes provided in the system bleed more and more air, thus weakening the mixture strength. The richness or weakness of air-fuel mixture is controlled by a throttle valve. When this valve is suddenly opened, that is, more than required air is allowed into the engine, it results in a weak mixture which is difficult to burn or is slow burning. This might result in difficulty in starting, 2. Stalling when idling, 3. Flat spot or hesitation, 4. Overheating, etc. Conversely, suddenly closing the throttle would cause an enriching of mixture or a shortage of air in the mixture. This would result in difficulties of burning, causing starting problems and release of unburnt fuels in the form of black smoke, which nowadays is a serious offense under the pollution control legislation. The unburnt gases can be monitored by a carbon monoxide analyzer.
A simple carburetor can provide a given air-fuel ratio at one speed only. The mixture strength or air-fuel ratio has to be exactly right, not only for steady operations at any one of the wide range of speeds at which engines can be run, but also to meet sudden changes when the vehicle is suddenly accelerated or braked. Now, in a country like ours, where vehicles have to be operated through a vast range of altitude and temperature, right from sea level up to 20,000 feet, or temperatures ranging from below 0 to 40 degrees, 45 degrees centigrade, the requirements of the carburetor become extremely complicated. To meet these demands and also the requirements of fuel economy, more and more complex carburetors are being designed and manufactured. There are two main types of carburetors in use today. The first type is called the variable venturi constant vacuum, and the other is the fixed venturi variable vacuum type. I'll try and show you one example of each of these carburetors. Mukandi ji, jara ek Solex और एक SU carburetor अंदर ले आइए.
Mukandi ji seems busy in detaching a carburetor. So let's also have a look as how to dismantle and reassemble one. In case of four-wheel carburetors, first remove the top of the carburetor. This is the pump jet. Remove the needle valve and check if it is dirty. The needle valve controls the inflow of petrol. Then remove the filter jet. Clean the filter or jali with a petrol syringe. Remove float control lever and separate the lever rod. Take out the float and check if it is damaged. Remove pump jet, which is connected with the accelerator. Remove other jets like slow running and idling jets. Start removing the top of the pump plunger assembly where a red diaphragm sits on a spring. Remove the choke system and wash it with petrol. Keep all the removed parts in a pan or tasla and wash them with petrol. After washing all the parts, these should be neatly laid on the workbench. Mop the carburetor body and the parts with a clean and dry cotton cloth. Start assembling them in order reverse from that of removal. That is, the part removed last should be fitted back first, and vice versa. Use new sealings while refitting the carburetor. Place the carburetor back on the engine and connect the fuel inlet pipe. Tighten all joints and fit the accelerator wire back. Fit the air cleaner back on top of the carburetor. In a similar way, a two-wheeler carburetor can be disassembled. First, remove the air filter. Disconnect the check nut on the accelerator wire and remove it. Remove the petrol inlet manifold. Next, remove the nuts fitting the carburetor in the engine housing. Remove the slide jet and piston. In two-wheeler carburetors, there is only one jet system, which combines both fast and slow-running jets. Remove other detachable parts one by one. Remove the float assembly. Take out the petrol filter or jolly. Start washing all the parts with petrol syringe. Clean them with a dry cotton cloth. And start refitting the parts in the order reverse to which they were removed. Let us take a look at the two types of carburetors. This is the fixed Venturi variable vacuum carburetor. Here the varying volume and speed of air through the Venturi tube creates a variable depression on the jet. This is the second type, called the variable Venturi constant vacuum carburetor, where the Venturi size is automatically adjusted to provide a uniform speed of air and a constant depression on the jet.
All fixed Venturi carburetors employ some kind of idling system to deliver mixture feed to the engine at very small throttle openings. This system is necessary because at minute throttle openings, the Venturi itself does not generate sufficient vacuum to make the car idle. The idling mixture adjustment in fixed Venturi carburetors is done either with an air regulating screw or a volume control screw. An air regulating screw adjusts the amount of air permitted to pass the cone of the screw into the channel connecting the idle jet and the idle discharge hole.
For a richer mixture, the screw is turned clockwise, bringing the cone of the screw nearer to its seating. Conversely, turning the screw anti-clockwise results in a weaker mixture. The alternative method is volume-controlled screw method of idling mixture adjustment. In this case, a fixed-size air bleed is used near the idling or pilot jet, while the mixture regulating screw, instead of controlling the amount of air entering the system, regulates the size of the idle discharge hole and thus the amount of fuel. The screw is therefore located so that its tapering point enters the idle discharge hole. To enrich the mixture, the volume control screw is turned anti-clockwise, and to lean the mixture, it is turned in a clockwise direction.
I hope that by now you have understood the basic functions and designs of carburetors. But to complete a full circle of this knowledge, we must look into the area of troubleshooting related to carburetors. For example, if the engine fails to fire from the cold, what faults could be responsible?
The cause may be an excessively rich mixture. This can be the result of prolonged use of the choke control. Pumping the accelerator in the endeavor to start will also cause a rich mixture. Excessive fuel can also be due to float needle defective, dirty or damaged needle valve setting, punctured or damaged float, a blocked inlet manifold drain pipe. Non-starting can equally be due to an overweak starting mixture due to 1. Petrol not reaching the float chamber, 2. Float chamber needle valve sticking and not opening, 3. Petrol leaks at pipe union, 4. Inoperative fuel pump, 5. Air drawn into suction side of pump. Conversely, it may happen that the engine fires when cold, but will not continue running. In such cases, either the strangler flap, that is the choke, is jammed or is not opening to required amount when the engine fires.
There could be another situation when the engine does not idle. In this case, assuming that the fault is not in the engine or ignition system, the fault has to be in the fuel system. Here the fault could be either with the idling adjustment, or there may be some kachra or dirt caught in the slow running or idling jet.
It should be adjusted at the normal working temperature by turning the idling screw so that the engine does not run heavily or vibrate or stop after moving some distance. If the engine still does not idle, it may be that 1. The air leaks due to worn throttle spindle and bearings, 2. Incorrect fuel level in the float chamber, 3. Blocked idling jet or passages, 4. Idling air bleed passages are choked.
Some manufacturers have now developed the concept of controlling carburation electronically by some sort of electrically actuated device. A major problem, however, is the difficulty in maintaining the system such that it is able to hold its accuracy and precision long enough to meet exhaust emission regulations. In any case, to maintain the engine in smooth running condition, the carburetor should be regularly serviced as per the vehicle manufacturer's recommendations.
The jets should be cleaned by blowing them out with air pressure. Never push wire through a jet hole, as this will damage the calibration. Passages can be cleaned out by removing the jet or jets from the passage and squirting a syringe filled with petrol into the hole from which a jet has been removed. Needle and ball valve assemblies can be washed in methylated spirits or petrol to remove sediment and gum. Any discussion on carburetors would be futile without discussing the air cleaner of a vehicle which protects the engine from abrasive matter, silences the air intake, and operates as a flame trap in the event of blowback. As already discussed, with a float chamber vented directly to atmosphere, a progressively rich mixture is produced as the filtering element becomes clogged. The air cleaner filter element should be cleaned with an air blower to remove any dust particles. In case the filter is made of sponge, as in modern motorcycles, it should be detached from the filter body carefully, washed properly with soap, rinsed, and dried in a dust-free atmosphere. Working on petrol systems calls for many precautions. As a safety measure, the battery should be disconnected to ward off the danger of a spark. Smoking of bidi or cigarettes nearby should also be forbidden. While opening the engine, rags should be used to catch any leaking fuel. On reassembly, all unions should be tight. Wherever applicable, new sealings and washers should be used to prevent leakage on reassembly.
Remember, many vehicle faults arise from a malfunctioning carburetor. A lack of proper carburetor maintenance can turn a good slave into a bad master.